This question is asked in gate 22 of instrumentation. This is from control system subjects and related to the stability and causality. You may say this is from signal as well, okay, the way the question is framed. Anyway, the question is a unity negative feedback control system has a loop gain Ls given by Ls equals to 6 by S into S minus 5. The closed loop system is, if you see the options, we are interested regarding the causality and stability. If you see the 4 options, so they are interested to know regarding the causality and stability of the given system. Okay, of which system? Of the closed loop system. This point is very important. So because it's a unity gain negative feedback system, so the closed loop system, if I say this is TS, then this is given by Ls divided by 1 plus Ls. The notation is Ls here, not GS. Okay, so if you find this closed loop transfer functions, because the question is for closed loop system, right? So that's why I'm first finding the closed loop transfer function. So this happens to be 6 by S into S minus 5 divided by 1 plus 6 by S into S minus 5. So let us multiply S into S minus 5 in both numerator and denominator. So this happens to be 6 by S into S minus 5 plus 6. So this is 6 by S square minus 5S plus 6. So this is 6 divided by, if I factorize this, so this will be S minus 3 into S minus 2. Isn't it? So this is what is the closed loop transfer functions. Okay, anyway, so let's have the pole zero plots. If I have the pole zero plots, so there are 2 poles and both poles, they are lying on the right half of S plane. So this is one pole, this is one pole. This pole location is 2 and this pole location is 3. Because there are 2 real poles, the number of possible ROC in this case, if I want to find, so there will be 3 possible ROCs. So let me show what are the possible ROCs. So one case, if I select the left-sided ROC, okay, this is what something it look like. If I select the right-sided ROC, so this is how it will look like. And the third possibility is in between them. The third possibility is in between them. So it is something like this. So in this case, so this is your case 1, this is your case 2, and this is your case 3. So in the first case, because the ROC including J omega axis, we can say this is stable case, but non-causal. Why? Because for causality, the ROC should be right of the rightmost pole. This is not happening. In the second case, so this is unstable. Why? Because it is not including the J omega axis, and this is causal because the ROC is right of the rightmost pole. Similarly, in the third case, if you see, this is unstable as well as non-causal. Unstable because this is not including J omega axis, and again the ROC is not the right of the rightmost pole. And if you see the options, so all these 3 possibility are there in the options, right? All the possibility are there, but so which one will be selecting? So here one by default assumptions will be making. So like all the control systems, they are by default the causal system. Okay, so if you refer any standard textbooks of control system, this is what you'll find in the introductory chapters. Like by default, all the control systems are causal system. Okay, so with that by default assumption, so the non-causal option first I'm eliminating. So non-causal option C and D are gone. So now if causal is what we have to select, so then the only possibility is the second one, because in the first case we have non-causal, third case also non-causal. So causal case means it will be unstable. So causal and unstable, if you see, this is given in option B. Option A anyway is not correct, because if any one of the pole lie on the right half of S plane, causality and stability simultaneously, it never happens. So the answer is causal and unstable. So it can be argued, sir, why can't be the other options are correct? Because the by default assumptions is the control systems is by default causal system. So with that assumption, the system is. This question is asked in gate 22 of instrumentation. This is from control system subjects and from state space topic. The question is the transfer function of a system is given. Okay. In the state space representation of the system, the minimum number of state variable in integer necessarily is. So, like this is a very standard informations. The minimum number of state variables, basically this is equals to the order of transfer function. So in general, in state space analysis, you must have learned this, that the minimum number of state variables that we need for state representation is nothing but the order of transfer functions. So what is the order? Order is basically how many poles are there in the system, or basically what is the order of denominators of the transfer functions. So that happens to be 3 here, right? There are 3 poles. So this is basically third order systems. So we need 3 variables. If this could have been a 10th order system, we need 10 state variables. So the answer is 3 for this. This question is asked in gate 22 of instrumentation. This is from control system subjects and related to the signal flow graph concept. The question is, the signal flow graph of a system is shown. The expression for y of s by x of s is. So as usual, we have a signal flow graph. What is the transfer function? The ratio of output to inputs. So here, first thing is you need to find how many forward paths are there, how many loops are there. Then you have to see touching loop, non-touching loops, and using the Mason's-Gain formula, you have to get the transfer functions. So as I see, there are only 2 forward paths. Forward path means the path from reaching to input to output. So this is one of the path, this straight, and the second path is this way. I cannot go this way because this arrow is this directions, right? So there are 2 paths. So P1, the straight path whose gain is G1, G2, and P2. So this is basically G1, G3. There are only 2 paths. How many loops are there? So delta 1, if I check the loops, so this is what is one loop, right? So if I say this is delta 1, this loop gain is given by minus of G2. Is there any other loop? Can this be a loop? No, because this arrow is this way. This is not a loop. Is it a loop? Yes, this is a loop. So if I say this loop gain is delta 2, so this is basically minus of G3, right? So now if I say what is the transfer function T of S, so that happens to be the first path is basically G1, G2. I mean for this one. To this, all the loops are touching, so you don't get anything here like 1 minus delta, so that will be basically equivalently 1. So you get G1, G2 plus. For the second path, this one, so this is G1, G3. So again, you don't get anything because again this path, to this particular path, all the loops are touching. So you don't get anything from this. Divided by 1, okay, then the corresponding loop gain. So there is a negative sign. So equivalently, this is G2 and this is G3. So because there is no non-touching loops and all, right? So this will be its corresponding transfer function. Very simple signal flow graph and very simple transfer function as well. If you check, so, okay, one more simple thing I am missing here. So there is a gain is specified here. This gain is 2, right? So 2. So this will be overall multiplied by 2. So if you check this, this is given by option A. So A is the right answer for this one. This question is asked in gate 22 of instrumentation. This is from control system subjects and related to the PID controller and the steady state error concept. The question is, a proportional integral derivative PID controller is employed to a stable control plant with transfer function PS equals to 1 by S plus 1 into S plus 2. Now the proportional gain is increased by a factor 2, the integral gain is increased by a factor 3, and derivative gain is left unchanged. Given that the closed loop system continues to remain stable with the new gains, the steady state error in tracking a ramp reference signal, okay, if you see the options like remain unchanged, decrease by factor 2, decrease by factor 3, decrease by factor 5. So one thing is clear. So what is being said is, so it's a unity negative feedback system, right? So is it given in the questions? Okay, so even though it is not given, so by default we take it, because whenever the steady state error concept we discuss, so by default we take it is unity negative feedback system. So if it is not given, by default that is what the assumptions will make. So that means the situation is something like this. So the PID controller, if I say the transfer function is C of S, this is what is the controller, and the plant is P of S. So this is what is the plant, and this is the inputs, and this is the feedback signal. So this is the arrangement is. But if I ask you what is C of S, C of S, I mean the PID controller transfer function. So very standard transfer function, which is Kp plus Ki by S plus this is Kds, isn't it? So in if you take LCM and if you try to simplify this, so this happens to be S square into Kd plus SKP plus Ki divided by S. right? This is what is the transfer function of the PID controller, or this is C of S. So what is the data first given is, so these are the gains, right? This Kp, Ki, Kd, these are the gains. So these gains are being altered, like here it is said that the proportional gain is increased by a factor 2. That means Kp become 3 Kp. Integral gain is increased by factor 3. That means Ki become 3 Ki. And derivative gain is left unchanged. That means Kd become again same Kd. So in such kind of cases, with this change in gain, what is the change in the steady state error? So first thing is, let us try to get a generalized expression of this steady state error. Okay. So, and that to be what kind of signal is given here? The ramp signal, right? So, in case of, if it is ramp signal, so the steady state error, okay, is given by A by the velocity error constant, which is limit S tends to 0, and this is S into, in this case, C of S into P of S. This is what is the open loop transfer function. And A is also, this is 1 here, because by default we take unit ramp case. Okay, ramp means unit ramp case by default. So this is what is the corresponding formula to calculate ESS. So ESS, if I try to simplify, this is limit S tends to 0, 1 divided by S into CS. CS is S square KD plus SKP plus KI whole divided by S. This is what is your CS, and PS is 1 by S plus 1 into S plus 2. So now if you see this S and S are being cancelled out, and if you substitute S equal to 0, so this term is gone, this term is gone, so this is gone and this is gone. So this implies ESS is equals to 1 by, from this you get only Ki, and from this you get only 2. Okay, ESS is equals to, this is 1 by 2 Ki, right? No, it is Ki, and from the second bracket term, how much you will get? 1 second. This is 1 in the numerator and in the denominator. So this Ki you will get as it is. So this is your Ki. And in this term, how much you get? So if you substitute S equal to 0, so you get it is 1 by 2. So that happens to be 2 by Ki. That means ESS is equals to 2 by Ki. Okay, so this is in general is the expression of the steady state error for this particular setup. Okay, that means what I can say in this case is ESS is proportional to inversely proportional to the integral gain Ki. That means ESS is independent of Kp and Kd. So in this case, if you see the what are the things has been changed. Proportional gain is increased by factor 2. So because of this, there is no change in the steady state error. Derivative gain is left unchanged. So anyway, in the expression of ESS, we don't have Kd term. So this is also not going to play any role. But the integral gain is increased by a factor 3. So this will play the role. So because there is a inverse relations, ESS is inverse to 1 by Ki. If the integral gain is increased by factor 3, that means this ESS will decrease by factor 3. So if you see decrease by factor 3 means this is given in option C. So C will be the right answer for this. So very simple and straightforward. Somebody should know what is the transfer function of a PID controller. By substituting the corresponding things in the expression of ESS, we are getting that ESS is coming 2 by Ki, right? So ESS is inversely proportional to integral gain. So even though there is Kp and Kd, whatever changes we make, so it is only depending on Ki. So because Ki is increasing by factor 3, then because of inverse relations, ESS will decrease by factor 3. So that is given in option C, and C is the right answer for this question. This question is asked in gate 22 of instrumentation. This is from control system subjects and related to the gain margin, phase margin concept. The question is, the Nyquist plot of a stable open loop system G of j omega is plotted in the frequency range of omega between 0 to infinite as shown. It is found to intersect a unit circle with center at the origin at the point P is equals to minus 0.77 minus 0.64 j. The point Q and R lie on G j omega, and assume values of Q equals to 14.40, R equals to minus 0.21. The phase margin and the gain margin of the system are. So basically this is a polar plot, not Nyquist plot, because the range of frequencies not from minus infinite to infinite. So, in a strict sense, this should not be an Nyquist plot, this should be polar plot. Anyway, this is again a standard model questions. So, the plot is given, and from the plot, we have to get the corresponding value of gain margin and phase margin. If you remember, what is gain margin and what is phase margin? So, gain margin is given by the relations 1 by magnitude of the transfer functions at phase crossover frequency, okay, at omega pc. And what is phase crossover frequency? The frequency at which the plot intersect the minus 180 degree axis, that is called the omega pc, the phase crossover frequency. Okay, so what is the phase crossover frequency, or what is the corresponding point with respect to phase crossover frequency? Because frequency is an implicit parameter here, right? But what is the corresponding point in this plot with respect to phase crossover frequency means, what we'll do is we'll check at what particular point this particular plot is intersecting the 180 degree axis. So this is what is your real axis. So you need to see at what particular point this black this one is intersecting the 180 degree axis. So that is nothing but your R. So this coordinate, you see, this is the point. And the location of R is given minus 0.21. So that means this length is basically 0.21, right? So basically that means what? The magnitude of the transfer functions at this particular frequency is basically 0.21. So if I substitute here 1 by magnitude of minus of 0.21, if you simplify this, this is 1 by 0.21, and if you see, so this happens to be 4.76. 1 by 0.21, this is 4.76. And if you see, this is given in option C and option A. That means option B and D are not correct. Note carefully that the gain margin is in the normal form, not in the dB form. Okay, that's why I am not taking 20 log in this case. So very simple. So we have identified what is the corresponding point with respect to phase crossover frequency. So phase crossover frequency is the point at which the plot intersects the 180 degree axis. So that is the point R. The plot is intersecting at point R to the real axis or minus 180 degree axis. So the corresponding magnitude with respect to point R is 0.21. So 1 by magnitude of 0.21 is basically 4.7. That is what is the gain margin. Now what is the formula to calculate phase margin? Phase margin is given by 180 degree plus the angle contributed by the transfer function, okay, at what frequency? At gain crossover frequency, omega gc. Now what is your gain crossover frequency? This is the frequency at which the magnitude of the transfer function become unity. So here if you see, this dotted circle is the unit circle. Now you need to check at what particular point the Nyquist plot, okay, is intersecting the unit circle. So that is nothing but this point P, right? You see at point P, the Nyquist plot, the black thick line is intersecting the dotted circle, that is the unit circle. That means at point P, the magnitude of the transfer function is basically 1. So you need to find what is the corresponding angle with respect to this point, okay? So for that, what I'm doing is, so I am just joining this point P to the origin, okay? So now you have to find what is this particular angle, this angle, because the angle is always measured from the 0 degree axis. What is this angle? So what is this angle? So this angle is basically, this is 90 degree, right? I mean this angle is 90, right? This is a 90 degree, and then I need to have what is this angle? What is this angle? So how do I get it? So because the location, the coordinate of P is given. P is basically minus 0.77 and minus 0.64 j. Okay, so let me erase the irrelevant part so that it will be easier for me to explain. Okay, so P, the location is given. So P is what is minus 0.77. That means if I have its corresponding projection to the this axis, so like this, like this. Okay, so this length is basically 0.77 and this length is basically 0.64, right? Because in the rectangular coordinate, the real axis is given, the point is minus 0.7. That means this length is basically 0.77 and this length is basically 0.64. Okay, now so what is the meaning of this? Then it is very easy to compute this angle. Which angle we are expecting? We are expecting this particular angle. Okay, So like if I say this angle is theta, so tan theta is equals to P by B. That is, P means this opposite side is basically 0.77, and okay, this is and B is basically 0.64, right? So if you see, this is what is your right angle triangle is. Okay, so tan theta, if I say this is theta, so P, this is P, and this is your B, right? B, this length is basically 0.64. So theta is equals to tan inverse of this quantity. So how much you get? So tan inverse of 0.77 divided by 0.64. Okay, so you compute this one, and if you compute, so this is happening to be 50.26. So theta is basically 50.26 degree. Take a calci and check it out. This is what you are getting. So what is this overall angle? So this 50.26 is this angle only. Okay, but what I was asking, so I was telling we need which angle we need. Basically we need this angle. So when I writing here this one, so this is nothing but this angle. Okay, so this angle is, this is 90 degree, and this is 50.26, and that too because we are moving in the clockwise directions, the angle should be in the negative one. If I had have moved in anti-clockwise this way, I would have taken positive angle. So this is basically 180 degree. Okay, minus of 90 and 50, so this is 140.26 degree. Okay, and if you simplify this, this is happening to be 39.73. Okay, so the answer is basically option A, because in C we have minus 39 points, and this is not correct. So A should be the right answer for this one. So a plot is given, and we need to find the gain margin, phase margin. By sticking into the standard definition of gain margin, phase margin, we obtain these values. The answer is option A for this. This question is asked in gate 22 of instrumentation. This is from control system subjects and related to the Bode plot and compensator concept. The question is, in a unity gain feedback control system, the plant transfer function P of S is given, is controlled by a lag compensator whose transfer function is C of S. The slope in dB per decade of the asymptotic Bode magnitude plot of the loop gain at omega equal to 3 10 per second is. Okay, so the situation is something like this. So like we have a unity gain negative feedback system. Okay, so it means we have a plant P of S, and along with this you have the compensator whose transfer function is C of S. So this is the typical scenario. Okay, and by default anyway we are taking negative feedback. So the transfer function P of S is given, transfer function C of S is given, and what you're supposed to find is slope in dB per decade of the asymptotic Bode magnitude plot of the loop gain. Okay, this point is important. That means, so we want the Bode plot of the transfer function T of S. T of S is nothing but product of P of S and C of S. If I ask you what is this one, so let us simplify this. This is 0.001 divided by S into 2S plus 1, then 0.01 S plus 1. This is your P of S, and into C of S, that happens to be S plus 10 divided by S plus 0.1. But while accessing the transfer functions, and if you want to have the Bode plots, it is wise to get the transfer functions like the factors like 1 by S plus some constant A form. This is what the format we expect, because from this data we can easily access the kernel frequency, right? And the questions which is asked, what is the slope at this frequency 3 per second, that also you can easily access. So my next approach will be to rewrite this transfer function in this format so that kernel frequency can be accessed. So the constant 0.001 is as it is. Then if I take 10 common from the this term, this happens to be 1 plus S by 10. Similarly, S is here, no problem. Then if I write this, so this can be written as 1 plus S by 0.5, right? Because 2S is equivalent to S by 0.5. Similarly, the next factors can be written as 1 plus s by 100. 1 plus s by 100. So that 1 by 100 is 0.01. Similarly, the next factors, which is s plus 0.1. Okay, so from this what you do is, so let us take the factor 0.1 common, because we don't have the 1 there, right? If I take 0.1 common, this happens to be 1 plus s by 0.1. So if I rewrite this one, this happens to be 0.1. I mean, this constant, and this constant together, it is 0.1 into 1 plus s by 10 divided by s into 1 plus s by 0.5. Okay, let me go in the okay, so let me write first this one, s plus 0.1, then this one 1 plus s by 0.5, and then 1 plus s by 100. So this is what is the transfer function T of s. For this particular transfer function, if we draw the Bode plot, so we are interested to know what is the slope of the plot at the frequency 310 per seconds. Okay, so if you see what are the kernel frequency, so kernel frequency so are 0.1, 0.5, 10, 100, and there is a pole at origin. So you know very well, one pole contribute minus 20 dB per decade slope and 10 contribute plus 20 dB per decade slope. So what is the situation is, so if we are targeting to know the information, so what is the slope at omega equal to 3 per second, you have to see what are the poles at 0 that might have came by the 3. Okay, so basically if I draw the Bode plot, what will happen? So this pole will contribute minus 20 per decade, right? Then after this pole, what is the next kernel frequency? That is 0.1, this one, right? So this will contribute minus 20 dB per decade. Then after this factor will come into picture. This will also contribute minus 20 per decade. Okay. Then what about this? So will it come before 3? Yes, because if I say this is your log omega axis, if I say this is the point with respect to omega equals to 3, before omega equal to 3, what will factor will come? This pole at origin will come, this factor will come, and this factor will come. This and this will not come by omega equals to 3, because this will come at 100, this will come at 10. So my interest is only these 3 factors. Okay. So this will contribute minus 20, this will contribute minus 20, and this will contribute minus 20. So by omega equal to 3, the net slope would have been minus 60 dB per decade. So this will be continuing like this till the next kernel frequency, that is 10. At 10, again plus 20 will be added because this is 0. Then the net slope will be minus 40. And that minus 40 will again continue till 100. At 100, again one more pole. So minus 60 it will be again. So, but the question is at omega equal to 3. So at omega equal to 3, only these 3 factors have contributed, and all are poles. Each pole is minus 20. So 3 poles means it is minus 60 dB per decade. So this answer is minus 60. So minus 60 is the right answer for this. This question is asked in gate 22 of instrumentation. This, you may say this is from controls or signal or from math, anything is okay. This is simply a normal, we have to find the magnitude and phase of a complex function. The complex number z is a plus jb by a minus jb, where a and b are greater than 0. Which of the following statement is true? It seems it's MSQ questions, right? The way this is being framed. So basically, if you see the options, so basically, the interest is to find the magnitude and phase. So z is equals to a plus jb divided by a minus jb. If I try to find its magnitude, so numerator becomes square root of a square plus b square. Denominator is also a square plus b square. If I try to find the phase for this term, you get tan inverse of b by a, and because of the denominator, so you get a negative sign, and again you get here tan inverse of minus b by a. Okay, so if you see this and this will cancel, so this is 1, and tan inverse function is an odd function, so this minus will come out here, so this become plus, so this is equivalent to 2 tan inverse of b by a, right? So if this minus will come here, so this is equivalently plus. Then if it is plus, Okay, then this become 2 tan inverse B by A. So magnitude is 1. Option C is correct. Phase is 2 tan inverse of B by A. So anyway, option B, tan inverse 2B by A, this is not correct. Magnitude is, you don't get this A square minus B square. So this is the answer, option A and option C.